One of the most important features of differential geometry is the Christoffel symbols. Powerful mathematical tools which allow us to describe curved surfaces and the geodesics upon them, and consequently which are requisite to any study of the theory of general relativity. But with increased power comes increased abstraction, and the danger of losing sight of the physical picture. Can we understand the meaning and purpose of these symbols without getting lost in the mathematics? This is Dialect with the Christoffel Symbols in Riemannian Geometry. In our prior video, An Introduction to Curvilinear Coordinates, we started with a flat manifold parameterized by an arbitrary curvilinear coordinate system, and then showed that we could characterize such coordinates through a very simple procedure. First, we drew a position vector from the origin of the manifold out to our point of interest along the coordinate curves. Then, we took the partial derivatives of this vector with respect to the coordinate variables u and v in order to get the basis vectors at that point. Then we permuted the dot products of these basis vectors in order to get the components of the metric tensor there. Before lastly taking the partial derivatives of both basis vectors with respect to both variables u and v. From there, we decomposed these basis derivatives into components of the parametric basis, before finally expressing those components as proportions of the basis vectors to get the Christoffel symbols. Now, the objective of doing all this was so that we could have a way of talking about the manifold from within the curvilinear coordinate system itself. That is, from within the parametric space where those curvilinear coordinates live. If this all sounds rather abstract, let's give it a bit more of a physical touch by imagining that we have an observer who is, in a sense, confined to the parameter space. What this means is that although they occupy some corresponding location on the manifold, they don't know anything about the distances or nature of the manifold itself. As of yet, they only really speak the language of the parameter space. However, if we give them two pieces of information at this point, the basis vectors and the Christoffel symbols, they will find their situation greatly improved. Indeed, let's say we hand them a basis vector EU, which points a certain direction along the manifold and has a magnitude of 2. What this basis vector tells the observer is that if they move a small unit of coordinate distance du in the parametric space, they will move twice that distance on the manifold in the direction that the EU vector is pointing. Likewise, if we give them a basis vector EV, which has a magnitude of 1.5, it tells the observer that if they move a small unit of coordinate distance dv in the parametric space, they'll move 1.5 times that amount on the manifold in the direction of the EV vector. These basis vectors thus convert the observer's coordinate distances and coordinate directions into manifold distances and manifold directions. Next, we offer the observer the Christoffel symbols, which tell them by how much and in what direction these basis vectors change across the manifold. As an example, let's say the first two Christoffel symbols, gamma UUU and gamma VUU, have the values -1/4 and +1/3 respectively. Then, if our observer travels a small coordinate distance du in the parametric space, gamma UUU tells them that their EU basis vector shrank in the EU direction by an amount equal to 1/4 times the length of the EU vector times du. while gamma VUU tells them that it also picked up a component in the EV direction equal to 1/3 times the length of the EV vector times du. The new EU basis vector thus points in this direction relative to the old. Meaning, if the observer continues to move along the same u-coordinate direction in the parametric space, they'll now know by what amount they've changed direction on the manifold, as well as the new amount of manifold distance a small step du will represent. The next two Christoffel symbols, gamma UVU and gamma VVU, give the observer this same information, only now with regards to how their v basis vector changes as they move along the u direction. Lastly, the remaining four Christoffel symbols tell the observer how their two basis vectors will change if they take a small step in the v direction as opposed to the u direction. Thus, if armed with the basis vectors and Christoffel symbols at every point, our observer has the ability to completely map out their manifold. Moreover, for any path taken in the parameter space, they can now determine what the corresponding path will be on the manifold. Now, on a flat manifold, there is always one special coordinate system, the Cartesian coordinate system, which has the unique property that, up to a scaling factor, coordinate distances and coordinate directions will always correspond to the real manifold distances and real manifold directions. Thus, on a flat surface, by no means is one ever required to use curvilinear coordinates. Although in some instances, such as with polar coordinates, a choice of curvilinear coordinates can be a useful one. However, when we move to a curved surface, it's no longer the case that a single coordinate system on that manifold can everywhere preserve manifold distances and manifold angles. Meaning, if we want to talk about a curved manifold, then we are required to use curvilinear coordinates. The good news is that the procedure for characterizing coordinates on a curved surface is essentially unchanged from that of a flat surface. Like before, we can get our basis vectors by drawing out a vector from some origin of our 3D space to our point of interest along the coordinate curves, and then taking the partial derivatives of this vector with respect to the u and v coordinates. Unlike before, however, these basis vectors no longer lie in the manifold itself, but rather are tangent to it, directed within the external space in which the manifold is embedded. Taken together, our two basis vectors thus form a tangent coordinate space, which again depicts how the parametric space infinitesimally transforms to the manifold there. Again as well, we can get to the Christoffel symbols by taking the partial derivatives of the basis vectors with respect to the u and v variables. However, since these basis vectors no longer lie in the manifold, neither will their derivatives. As an example, let's take the difference between this EU basis vector and its nearby neighbor in the u direction. Indeed, we can see that the resultant delta EU vector here isn't directed along the plane of the manifold as it was in the 2D case, but clearly points to some degree into the manifold itself. This is because some of the change of the EU basis vector here is brought about by the curving of the manifold itself, rather than just being due to the curving of the coordinates. To distinguish between these different cases of curvature, we can decompose our delta EU vector into one component which lies tangent to the manifold and one component which lies normal to the manifold. Now, this normal component is brought about by the curvature of the manifold itself through the 3D space. But since, as of the moment, we're not yet interested in the curvature of the manifold, we'll simply throw this component out and only worry about the change which occurs relative to the surface of the manifold itself, i.e., those components which lie in the tangent plane. Indeed, if we compare the change in our basis vectors along a curve, such as the change in our EV basis vector along the v-coordinate curve, and the change in that vector lies entirely normal to the surface, this tells us there was no change of our basis vector within the surface itself, and hence that the direction and magnitude of this basis vector remains unaltered with respect to the manifold along that coordinate path, even if it was technically altered through the 3D space. We'll call such a path along our manifold a geodesic. All right, let's go ahead and turn this tangential delta EU vector into a proper partial derivative. That is, take its limits per an infinitesimal change du in the parametric coordinate. Then, to find the remaining derivative vectors, we first need to compare the EV vector with its neighbor in the v direction. But as we already saw, that led to no tangential change. And so the dEV dv derivative is 0. Next, to find dEU dv, we need to compare the EU basis vector with its neighbor in the v direction. Doing this leads to a change that lies entirely in the tangential plane. Lastly, we need to compare the v basis vector with its neighbor in the u direction to find dEV du. Doing this yields the same vector as dEU dv. Once this is accomplished, we need to further decompose these derivative vectors into components of the parametric basis. Fortunately, both these vectors already point along our basis directions. Thus, all that's left to do in order to get our Christoffel symbols is to express these vectors as proportions of the basis vectors. Indeed, we can see that this vector here spans approximately 2/5 of the length of the EV basis vector. So its Christoffel component is roughly 0.4. This vector, meanwhile, spans about half the length of the EU basis vector and is pointed in the opposite direction. So its Christoffel component is roughly minus 0.5. Now, at this point, with our toolkit of basis vectors and Christoffel symbols sorted out, we'd essentially be done characterizing our manifold via our parametric coordinates. However, an issue remains, which is that we found these mathematical objects extrinsically. That is, by referencing the external 3D space in which our manifold is embedded. Indeed, if we were fine with referencing this external space, then by expressing our position vectors x, y, and z components as multivariable functions of the parametric variables u and v, we could calculate all the requisite mathematical objects from this vector alone. As an example, taking our manifold to be a unit sphere, we could parameterize its surface via spherical coordinates, with v being the polar angle to any point on that surface, and u being the azimuthal angle. Then, writing our position vector as uppercase V equals sine v cosine u, sine v sine u, and cosine v, the basis vectors and Christoffel symbols at any point follow pretty simply from the partial derivatives of this vector, via the formulas developed in the last video. But what if we don't necessarily have easy access to this position vector v? That is, what if we don't want to explicitly refer to our external space? Indeed, let's return to our observer, now on our curved spherical manifold, and treat him in the sense of a flatlander unable to reference their external 3D space. This means we can't give them the basis vectors like before, since those have three-dimensional components. So what can we do? Well, instead, we can start by giving them the metric tensor. The metric tensor contains only scalar values, and hence does not explicitly reference the external space. Yet, it still contains all the requisite information about our basis vectors. This first component tells the observer the magnitude of their EU basis vector squared, while the second component tells them the magnitude of their EV basis vector squared. And lastly, these third and fourth components tell them the dot product of the two basis vectors with one another, or the magnitude of the EU vector times the magnitude of the EV vector times the cosine of the angle between them. Thus, just like before, if our observer knows the values of the metric tensor at any point, they can deduce how much manifold distance a small coordinate step du will translate to, how much manifold distance a small coordinate step dv will translate to, and what the manifold angle between the u and v coordinate directions will be at that point. However, if they continue along the u or v coordinate curves, they no longer will be able to use the 3D basis vectors to calculate the Christoffel symbols, and will be unable to describe how their path on the manifold is changing. Our observer thus needs a new way to calculate these Christoffel symbols. But where does this information come from if we can't resort to examining changes within the three-dimensional space itself? Well, part of this information is already lodged in the metric tensor itself. Indeed, some simple calculus shows that the derivatives of the metric tensor components are related to the derivatives of the basis vectors. However, since the metric tensor only holds information about the magnitudes of our basis vectors and the relative angle between them, it tells us nothing about how neighboring basis pairs are oriented relative to one another. For this, we need something formally called the Levi-Civita connection. In this context, the Levi-Civita connection is simply the requirement that our coordinate curves close. That is, if our neighboring v basis vector in the u direction changes by some amount, then the neighboring u basis vector in the v direction also needs to change by this same amount. Thus, by setting deu dv equal to dev du, we ensure that these two basis vectors meet, and hence that our parametric space fully maps the manifold space. Now, when you take the derivatives of the metric components, then impose the Levi-Civita condition, and finally solve for the Christoffel symbols, you'll arrive at the following 6 independent equations expressing the values of the Christoffel components purely in terms of the metric tensor and its inverse. These equations make no explicit reference to the external space, and thus allow our observer to determine how their coordinate curves are changing over the manifold from within that manifold itself. Now, these 8 equations can be more succinctly summed up with this single equation, which features permuting indices and generalizes to any number of dimensions. Here the I, K, and L each stand in for specific parametric variables, while the M, which appears in both the lower and upper indices, indicates a summation over all the parametric variables. Now, while this equation certainly looks frightening, on the whole, it's actually a relatively simple equation that captures a large number of trigonometric relations. Indeed, it neatly encapsulates all the ways 3 neighboring pairs of basis vectors can be altered while still ensuring that these vectors come together and close. Briefly, we can get a better understanding of how this works by considering case-by-case scenarios of how different changes in basis vectors will affect one another. Starting with the most simple case, is the one, of course, in which there is no change in our basis vectors. Here, the metric values are constant, and each vector retains its same magnitude and direction. Consequently, in this scenario, all 8 Christoffel symbols are 0. The next most simple case entails a change in length of one or both of the exterior basis vectors. Here, the growth or shrinking of these vectors induces no rotation, and at most 2 Christoffel symbols are activated. In the next case, we begin with our basis vectors oriented orthogonally, and then change the length of one of the interior vectors. In this case, in order that the vectors close, the opposing basis pair must be rotated through an amount as to compensate for that change in basis length. This activates 3 total Christoffel symbols, 2 of which are equivalent. In our fourth case, we again consider orthogonal bases, and this time change the length of not just one interior vector, but both interior vectors. This requires that both basis pairs are rotated, and consequently 6 total Christoffel symbols are activated, 2 pairs of which are equivalent. Our fifth case is that of a simple skewing of one of the basis pairs. This skewing only affects a single basis vector, but requires that 2 Christoffel symbols are activated. Finally, in our sixth case, we begin with the basis pairs already skewed with respect to the manifold, and then change the length of one of these pairs' interior basis vectors. As before with the orthogonal case, this will require that the opposing basis pair be rotated in order to compensate for the change in length. However, unlike before, due to the coordinate skewing, there will still remain a gap and the vectors will not yet close. We are thus forced to also rotate the pair which saw the change in interior vector length. This immediately results in all 8 Christoffel symbols being activated. These 6 essential cases, which can be combined into more complex ones, encapsulate all the pertinent constraints of our Christoffel equation. Now, it took numerous pages of scribbling out diagrams and trig formulas to verify that these were indeed the precise geometric relations entailed by this equation. And while it's quite astounding the wealth of trigonometry that's handled so simply and so effectively with the use of quadrances and dot products, we wouldn't recommend going that route. Instead, to get a better handle on why this equation looks the way it does, let's instead start with a single derivative vector, say dEu du, whose magnitude we'll label as a, and let it have this orientation and length relative to its corresponding EU-EV basis. As before, we'll break this vector into components of the parametric basis. Now, if we want to solve for, say, gamma UUU, the key is to remember that its value is simply the length of this component, which we'll label b, over the length of the EU basis vector. Now, if our bases were perpendicular, then this length b would simply be the projection of the derivative vector onto the EU basis, or dEu du dot EU over the magnitude of EU, which leads us directly to the formula for gamma UUU obtained in the last video. However, if the bases are not perpendicular, then the projection of dEu du along the EU direction does not give the full correct length of b, as there's still some extra length due to the skewing of the bases. This extra length is the projection of the v component, which we'll label as c, onto the EU basis. The value of the Christoffel symbol can thus be written as the projection of a onto EU plus the projection of c onto EU over the magnitude of the EU basis vector. Now we want this equation solely in terms of the projections of a. So after exploiting some trigonometric properties of our triangle, we can rewrite this equation as the projection of a onto EU over the magnitude of EU times sine squared theta minus the projection of A onto EV over the magnitude of EU times sine squared theta times cosine theta, where theta is the angle between our basis vectors. Further rewriting our projections as dot products adds an additional magnitude EU term in this denominator and a magnitude EV term in this denominator. Next, we want to express everything in terms of the metric. From the derivatives taken earlier, and by expressing the inverse metric in terms of the basis magnitudes, we can note that this dot product here equals 1/2 dGUU du, while this quantity here equals GUU inverse. Meanwhile, this quantity here equals GUV inverse. And finally, this dot product, which can be found by imposing the Levi-Civita condition, equals 1/2 times 2 dGUV du minus dGUU dV. We see we now have arrived at the expression for gamma UUU, and likewise we can derive our other Christoffel symbols in a similar manner. Now this geometric derivation allows us to interpret our generalized Christoffel equation in a very simple way. First, we can recognize that the 1/2 here is required as a correction factor due to using metric quadrances instead of lengths. Next, we can recognize that the inverse metric term here essentially functions to convert our manifold units back into units of the parametric space. And lastly, we can recognize that this expression in parentheses is twice the dot product of the derivative vector in question with the m basis vector. If our bases are skewed, we need to sum the contributions from each basis dot product in turn, in order to get the total correct length of the Christoffel component vector. But if the bases are not skewed, then only the m equals I term ends up hanging around. Now that we hopefully have a better understanding of where this equation comes from, let's have our observer use it to calculate the Christoffel symbols on their two-sphere. Just as before, we'll parameterize the surface with the coordinates u and v, which correspond to the azimuthal and polar angles. Now, instead of giving our observer a 3D position vector v, we'll give them the metric tensor, whose non-zero components in this instance are GUU equals sine squared v and GVV equals 1. Off the bat, we can note that the zeros in the diagonals indicate our basis vectors will be everywhere perpendicular, while GVV equals 1 tells us our v basis vector magnitude will be everywhere constant. Additionally, let's note that since this is a nice diagonal metric, its inverse is simply the reciprocal values, that is, GUU inverse equals 1 over sine squared v, and GVV inverse equals 1. Okay, let's start by calculating gamma UUU and gamma VUU, detailing how our EU basis vector changes in the u direction. Gamma UUU is nice and easy. All the indices become u's except for this m index here, which again indicates that the equation is supposed to be summed over both variables. Thus, after expanding out the expression, all that's left to do is plug and chug. Here, GUV inverse is 0, so this whole term goes away. Additionally, each of these dGUU du terms are also 0, since the expression for GUU does not depend on u. Our first Christoffel symbol, gamma UUU, thus equals 0. Next, to calculate gamma VUU, we again bring up our general expression, and, looking for the i's in this equation, we replace them with v's. Then we replace the k's and l's with u's. Lastly, expanding out the m summation gives this expression. Again, since we know GVU inverse equals 0, this first term vanishes. Within the second term, these two dGVU du terms are also 0, leaving us with just this expression. The derivative of GUU with respect to v is 2 sine v cosine v, and GVV inverse equals 1. So plugging those values in yields the value of our second Christoffel symbol, minus sine v cosine v. Now, by repeating all these steps for gamma UUV and gamma VUV, which detail the change of the EU basis vector in the v direction, we'll find gamma VUV is 0, while gamma UUV reduces to this following expression. dGUU dV is again 2 sine v cosine v, while GUU inverse is 1 over sine squared v. So this expression reduces to the cotangent v. We thus have our third and fourth Christoffel symbols. Now, proceeding along this line, it's not hard to show that gamma UVV and gamma VVV, which detail the change in the EV vector in the v direction, will both equal 0. And finally, by exploiting the Levi-Civita condition, we can cheat with these last two Christoffel symbols by remembering that they must also be equal to cotangent v and 0. Alright, with all 8 of the Christoffel symbols calculated, we can now see that our two-sphere represents case number 3 among our Levi-Civita constraints. That is, if our observer moves in the positive v direction, which here, due to our polar angle convention, is southwards along the manifold, the growth of their u-coordinates there requires that the coordinates in the latitudinal direction be rotated up. Now, in an earlier video, we saw that case 3 of our constraints was also represented in the scenario of polar coordinates on a flat manifold. Indeed, examining our observer's local picture, we see the coordinate system here within this infinitesimal region precisely matches that of polar coordinates on a flat manifold. Yet, globally, our two-sphere is clearly not a flat manifold, leading to the question, how can our observer distinguish between these two cases? That is, if our Christoffel symbols primarily describe what case of curvilinear coordinates our locally flat infinitesimal region of the manifold exhibits, can they be used to determine even more? Indeed, having given our observer the tools to intrinsically map out their manifold, in a sense, we now want to reverse the process and ask, is it possible to extract extrinsic information about our external environment from intrinsic data alone? Well, attempting to answer that question is going to lead us to some very interesting concepts, including that of connections, parallel transport, and ultimately, the notion of curvature. And we'll find that, once disentangled from their layers of mathematical abstraction, these concepts will point us towards some very interesting insights about general relativity. This has been Dialect. As always, stay tuned.